Let's look at this set. In a conference hall, there are exactly 6 switches, switch 1 through switch 6, and 2 lights, light A and B, with each light connected to exactly 3 distinct switches. Each light connected to exactly 3 distinct switches. So 6 switches are distributed between light A and B, each light having 3 switches. Changing the state from on to off or from off to on of any one of the 3 switches connected to the light exactly once will change the state of that light from on to off or from off to on. When all the 6 switches are in the off position, the 2 lights are both off. Now see, I'm saying let light A be turned on by switch 1, switch 2, and switch 3. And light B be turned on by switch 4, switch 5, switch 6. If all of them are off, sorry, one extra F here. At this time, the overall light is also off. But if I change the state of one of these switches, let's say switch 2 changes its state. From off, it changes to on. And switch 1 remains off. And switch 3 remains off. Even that will change the state of light A. This will turn on. See, changing the state from on to off or from off to on of any of the 3 switches connected to the light exactly once. I've changed the state of switch 2. Will change the state of that light. It has changed the state of that light. Which is another way of saying, if I did it again, if this was off and this was on and this was on, see now switch 3 has changed state, this will again turn off. Now if I change the state of switch 1 again, this is on, and this is on, light would be turned on. In other words, can I say whatever switches are linked to you, whatever switches are linked to a light, odd number of switches need to be turned on. See here, exactly 1 switch is turned on. Here, exactly 3 switches are turned on. When you have 0 turned on or 2 turned on, the light is off. When you have 1 turned on or 3 turned on, the light is on. This is a critical interpretation that you have to do in order to make sense of this set. Okay. Let me get rid of this writing. This was only for explanation. There is further instruction. If only switches 1, 3, and 5 are on, and only light A is on. Okay. This means, see, light A can either have 1, 3, 5, or only 1 is linked to light A, or 3 is linked to light A, or 5 is linked to light A. Which is to say, if all 3 are on, if all 3 of them are linked to light A, then A will be turned on. If only 1 is linked to light A, then A will be turned on. If only 3 is linked to light A, then A will be turned on. If only 5 is linked to light A, then A will be turned on. If 2 of them are linked to light A, then A would be off. Because for a light to be on, odd number of switches linked to it should be turned on. Correspondingly, let's say, if A had 135, B should have how much? The 246. Also, with this one, can we see if only 1 is linked to A, 3 and 5 have to be here. With only 3 linked to A, 1 and 5 have to be here. With only 5 linked to A, 1 and 3 should be linked to B. We have read only this far. Next line. If only switches 2, 5, and 6 are on, only light B is on. If 2, 5, and 6 are on, can you see that helps us eliminate this case from consideration? This cannot be a possibility because 2, 5, and 6, it tells me 2 lights linked to B are on, yet light B is on. 2 switches linked to light B are on, yet B is on. That is not possible. So this cannot happen. This cannot happen. Okay. Now let us look at this. 2, 5, and 6 are on and light B is on. In this case, what would happen? 2, 5, and 6 are on. 5 we know is already linked to B. and 3 is also linked to B. So all 3 switches linked to B are not on. Exactly one linked to B is on. If exactly one linked to B is on, these two here, 2 and 6 that are on should be linked to a 1, 2, 6 and 3, 5, 4. This case will get created. Similarly, let's look at this one here. 2 and 6 should be with A and 1, 5, 4 should be with B. Then finally, let's look at this one now. Between 2, 5 and 6, we know this is linked with A. In this case, we know 5 is linked with A. So either 6 is linked with B or 2 is linked with B. Either 6 is linked with B or 2 is linked with B. So we make two cases, 2 or 1, 3, 6 with 5 here. Now 1, 3, 2 is done here. So 5, 4, 6 here. 1, 3, 6 is done here. So 5, 2, 4 here. These are the 4 possibilities that we have right now. If 1, 3, 5 is on, only 1 here, only 3 here, only 5 here, only 5 here. Yes, first condition is met. If 2, 5, 6 are on, only 5 here, only 5 here, only 2 here, only 6 here. Yes, so this is also. Now the last condition which helps us narrow it down to one specific case. If only switches 1, 3, 6 are on, only light B is off. If 1, 3, 6 is on, if 1, 3, 6 is on, light B is off. At this time, can I rule out? In this case, 5 to 4 will go, because if 1, 3, 6 are on, all 3 lights are on, all 3 switches are on for light B, yet it is switched off. So this cannot be a possibility. This is ruled out. How about this one? Out of 1, 3 and 6, only one is linked, only switch 1 is linked to B, yet light B is switched off. So this cannot be a possibility. Out of 1, 3, 6, only 3 is linked to B, yet B is switched off. So this cannot be a possibility. So the switches and the lights that they are linked to can be uniquely identified as such. B is linked to 1, 3 and 2, A is linked to 5, 4 and 6. Okay, now let's get to individual questions. Which of the following switches is connected to light B? Switch 1 we know is connected to light B, so option A. Next, 5 of the 6 switches were on while the 6th was off. If 5 switches are on and 6th is off, one light will be on, one light will be off, because three switches will be on for one light and 2 switches will be on for one light. If only light B was on, which of the following can be the switch that is off? If light B is on, all 3 switches of B have to be on. The switch that is off has to be of light A. So 1, 2, 3 will be on. 1, 2, 3 will be on. Switch 4 can be off. So option D. Next. Ram, a 5-year-old kid, entered the conference hall. And on entering the hall, he saw that light A was on while light B was off. Okay. I am recording this as, right now, odd switches are on here and even switches are on here. Odd switches are on here and even switches are on here. Okay. He pressed, that is, changed the state of switch 1 once. Can I say, if he changed the state of switch 1 once, this has changed? I will represent a switch that is changing its state with an arrow. State of switch 1 once, this has changed. If he changed the state of switch 2 twice, whether it was off or on, it has returned to the original. If it was on, first change will take it to off, second change will take it to on. So there is no change in switch 2. Switch 3 thrice. So one change, second change, back to original. Third change, definitely changed. This is also changed. Now see, for every change that happens, you can also, 1 is changing and 3 is changing. 1 is changing and 3 is changing. Now, if 1 is changing and 3 is changing, can I say previously even switches were on? Previously even switches were on. After 1 changed, if this has also changed and this has also changed, whether it turned from on to off or off to on, can I still say even switches will still remain on. Even switches will still remain on. Either previously two switches were on, or previously zero switches were on. Even when I change the state of 1 and 3, still even number of switches will be on. You can go ahead and potentially look at it this way. Let's say if the off I'm representing with minus and on I'm representing with plus. This was minus earlier, this was minus earlier, this was minus earlier. All of them are off. State has changed, turn to plus, remains at minus. We have exactly two switches turned on. This would not work. Or let's say the initial state was this was switched off, this was switched on, this was switched on. State has changed, turn to plus. State has changed, turn to minus. State has changed. Oh, sorry, state has not changed, remained at plus. Two switches are turned on, it will remain off. Or any other case you check. Let's say this was plus, this was minus, this was plus. Now, state has changed, turn to minus. State has changed, turn to minus. This remains at minus. Light will continue to remain off. Regardless of what you do, B will continue to remain off. B will continue to remain off. And this is only up until this part. This is only up until this part. So B is going to be off after all the wonderful work that Ram, the 5-year-old kid, is doing. Next, for switch 4, he changes the state 4 times. If he changes the state 4 times, it will re-achieve the original situation only. The state is not changing for 4. While the 4 times and so on. So for switch 5, he must have changed the state 5 times. For switch 6, he must have changed the state 6 times. Hopefully, you can fathom by now. The odd switches, their state has to change. The even switches, their state wouldn't change. Previously, light A was on. So odd number of switches were on. Odd number of switches were on. But because 5 is changing its state, it will now turn to even number of switches will be on. Even number of switches will be on. Again, you can go ahead and check it with the plus minus representation. Previously, if it was this, it will turn to minus plus plus, and therefore light A will be off. Or if it was this, plus minus minus, in this case, light A will be on. Switch situation has changed, so turn to minus minus minus. Or if earlier the situation was minus plus plus minus plus plus, then it would be off, no? Minus plus minus, minus plus minus. If this was the situation, then light A would be turned on. Because 5 has changed its state, it would turn to plus, plus, minus. Regardless of what case you take, can you see, finally, you will definitely have even number of switches that are turned on for light A. Which is another way of saying, not only B, A will also be off. Eventually, A will also be off. If A will also be off, that helps us answer the question. Which of the following is true after Ram pressed all the switches in this manner? Light A is on, B is off, wrong. Light A is on, B is on, wrong. Light A is off, B is on, wrong. Light A is off and light B is off. Both the lights would have even number of switches turned on, and therefore both of them would be off. Okay, last question. Ram, a 5-year-old kid, entered the conference hall, and entering the hall, he saw a light. He saw that light A was on, while light B was also. He pressed, that is, changed the state of switch 1 once, switch 2 twice, switch 3 thrice, and switch 4 times, and so on. So basically, this storyline is being told to us again. After this, he found that exactly one of the switches was now on. Exactly one of the switches was now on. If exactly one of the switches is now on, pay attention, if exactly one of the switches is now on, which of the following switches were definitely on when he entered the hall? See, if exactly one of the switches is now on, it would mean, see, he saw that light A was on while light B was also on. Previously, light A was on and light B was off. So this time working has changed slightly. Working has changed slightly. You have to get rid of all this working. Again, back to the processing wise, light A was on and light B was also on. Both of them are on initially. Both of them are on initially. If both of them were on initially and he changed the state and everything he did, one will change its state, switch 1 will change its state, switch 3 will change its state, switch 5 will also change its state, 2, 4, and 6 will not change their states. Which 4 times. After this, he found that exactly one of the switches was now on. Exactly one of the switches was now on. Okay. If exactly one of the switches are now on, it would mean for one of these, 3 are off. For between A and B, for the 3 switches that they have, and for the other one, 2 are on, 1 is off. Okay. So who has all 3 off and who has 2 on, 1 off? Okay. Let's see. T off. If B was on, if B was on initially, then it can either have all 3 switches turned on. It can have all 3 switches turned on, changing the state. This turns to minus, this turns to minus, this remains plus. So now B will be turned on finally. And here, so now finally, if there was only one switch that was on, so if this is plus, this has to be, I don't know in which order, but there, oh no, I know in which order. All 3 of them have to be minus. All 3 of them have to be minus. If all 3 of them have to be minus, and 5 is the only one that has changed its state, then 5 was initially plus, and then 4 was minus, and 6 was also minus. In this case, this is an acceptable case that we have created. This is an acceptable case that we have created. Yes. Okay. In the other variation, let's say B was on with 1 plus minus minus. Now the state has changed to, this has turned to minus, this has turned to plus, this has turned to minus. We have got our plus. We have got our plus. So we come here, we have got our plus, so all 3 of them have to be minus. If all 3 of them have to be minus and 5 is the only switch that has changed its state, this has to be plus, this has to be minus, this has to be minus. Yes. So if I look at just these 2 cases, the only possibilities are 1 and 5 as my answer. Okay, let me try out another case. 5, 4, 6 and 1, 3, 2. Hopefully, the more smart ones amongst us must have caught on. Here I put a 1 as plus. In this case, let me put this as plus, this is minus, this is minus. If I turn this around, I would get this as plus, this is minus, this is minus. I've got my 1 plus here. So here it would be minus, minus, minus. I know 5 has changed its state, 1 has changed its state, 3 has changed its state. If 5 has changed its state, previously it must be plus. These 2 must be minus only. So now, when I look at, let's say, call this case A, let's call this case B, and let's call this case C. Regardless of which case you take, here you had switch 5 as positive, 1 as positive, 3 as positive, and 2 as positive. Here, only 5 and 1 were positive. Here, only 5 and 3 are positive. Regardless of which case you take, can you see? Switch 5 remains positive at the beginning of these operations, regardless of which case you take. And therefore, the answer to the final question has to be option D, switch 5, and that is the entirety of the set. This is what is known as binary logic, switch on and off. Ideally, binary logic questions we represent with zeros and ones. But here, because the switch numbers themselves were given, switch 1 and switch 2, using 0 and 1 was not very ideal. So I had to use plus and minus. First, we had to figure out which switches were linked to which light, and then whatever further processing, all the case working had to be done. That will be all for this set.